All right, guys, so today we're talking about volume. And to talk about volume, I want us to go back to the very, very first day of school. So I want you to think about those two vases that I had you try to figure out the volume. Do you guys remember that activity where I just basically handed you these two things? I was like, hey, find the volume. Okay, well, today we're going to talk about the actual mathematical process for figuring out how to find the volume of odd shapes. Like if we were to have a perfect cylinder, we know that we could find the volume simply by using the same formula for the volume of a cylinder, pi r squared times height. But the problem with these two types of vases is that our radius is not the same as you go from start to finish. So our radius starts out wide, it gets kind of narrow, and then gets wider and back to narrow. And over here, it kind of has a hyperbolic shape if you look at it, okay? So what we have to do is we have to think about, if I were to take this vase, and I'm going to take each one, and I'm going to lay it on its side. Okay, so I'm gonna look at this first one. Okay, imagine for a second that I laid the vase on its side and I put it on a coordinate plane. All right, and then what I want to do is I want to come up with a function that goes with the curve of the edge of my vase. Do you guys see that? So I'm going to imagine that this right here is some function. Okay, and this is going to be some function for my radius, because I'm going to envision that I've got a vertical line through my vase. I mean, pretend that that was vertical for a second, and that my function would determine what the radius is of my vase. So I already have this kind of typed up in an equation form over here. So you're probably looking at this going, wait, what? This doesn't look right. Let me adjust this just a bit. There we go. So I've got my function here. Let me keep going a little bit. I've got my function here. And what's happening is, if I were to take this function and let's say I were to rotate it around the x-axis, that would essentially create the overall shape of my vase. Let me show you what I'm talking about here. Okay, right now I've got my function, okay, and I just put it along the x-axis. Basically, I took the vase and I rotated it sideways. Okay, and so then the distance, like that was originally, this was a vertical line through my vase. Now it's a horizontal. But if I were to take this curve and rotate it around the x-axis, notice I create a shape that looks very similar to the vase that we have. It's not a perfect portrayal of it, but this is pretty darn close. Okay? So now what we're going to do is we have to find the volume of this thing. Okay? So let me stop revolving that for just a second. So what we have to do, okay, is think back to when we first did volume by, think back to when we did area. Okay, let me go back to this for a second. So let's think back to area for just a second. When we did area of a curve, oh, hang on one second. When we did area, remember how I always have my basic function that I start with here. Okay, and essentially what we did is that we started out with little rectangles. Okay, well, I should have drawn that first one. We started out with rectangles that we used to approximate the area. Okay, that's what we started with. You guys remember that process? Okay, then after a while we were like, all right, well, let's make it more accurate. Instead of having big rectangles, we essentially made the rectangles so infinitely small that we basically had all of these teeny tiny little lines. Okay, now remember, lines actually have no width, but if we add up all of these y values together, it creates the area under this curve. Essentially, our area accumulates as you go from left to right. Okay, well, so now with volume, instead of adding these little lines together, so in area, adding a one-dimensional thing creates a two-dimensional area. So in volume, since it's three-dimensional, what we have to do is we have to combine two-dimensional area together to create volume. I'm going to repeat that one more time. So to find volume, we combine or accumulate two-dimensional areas, an infinite number of them, and that's going to create volume. And here's what I mean by that. So if you look at this shape right here, okay, so I'm going to basically pretend, actually, let me go ahead and just revolve this one time so we can see the shape. Okay, so I actually keep going all the way around. My bad. I didn't mean for it to do that, but that's okay. All right. So now we've got the whole thing drawn. Perfect. So you'll notice already it's got all of these circles kind of drawn for you, okay? So in area, we had lines that we added together. But in volume, we are taking all of these circles. So we have a circle on the end, and then we have an infinite number of circles all the way through from the left all the way to the right. We have an infinite number of circles that we can add their areas together, and by doing so, we actually create volume. Now the catch is, how do we actually find the area of each individual circle? Because if you notice, the area of this circle is very different than the area of this circle, and also different than the area of this circle down here. Well, luckily, we can write the radius as a function of x, because our radius, as you go from left to right, our radius is changing. It's getting wider, it's getting narrower, and that's just for this example. It's going to be different every time. So what we do is we want to look at the radius themselves, or itself. So let me see if I can get a little pen tool here. Just want to see if I can draw on this thing. Okay, so basically what I want to do is, when we did area, okay, I found the area by looking at the integral from a to b of my function with respect to x. Okay, that's a very basic way we did area. Okay, now, what this does is I add up an infinite number of y values together, or an infinite number of the heights of my whatever it is, okay, my function. Now for volume, it's going to be a little bit different. Okay, what we're going to do is we have to think about the fact that we are adding together a bunch of circles. Okay, well, before I get to that, what's the area of a circle? Hopefully we all know that that is pi r squared. Okay, so my volume, I'm going to start with pi, but I'm going to integrate from start to finish, from a to b. Instead of r squared, okay, I'm going to think of r as a function of x. So that's going to be f of x quantity squared dx. Okay, so for area, we just simply integrated our function from a to b. Okay, if I were just simply finding this blue area right here, that's what I would do. But now, since I'm taking that area and essentially I'm rotating it around the x-axis, okay, to create a solid shape, now I am trying to find the volume by essentially integrating the area of a circle. The area of a circle is pi r squared, but I have an infinite number of circles, and the radius for each circle is different. So to account for that, I use the integral process by saying the integral from a to b of my function squared, because remember, this represents my radius, okay, my radius squared dx, and then pi, because it's pi r squared for the area of a circle. Okay, I hope that makes sense. Let me show you another situation here. So think back to the other vase that we had. So we had this other vase that was a little bit different shape. Okay, if I were to rotate this around the x-axis again, okay, you revolve it around the x-axis, you create this solid shape. Now I realize, let me back up for a second. I realize the vases that we were using were hollow. Okay, for right now, for simplicity's sake, we are pretending that the vases are solid. Okay, that they are a solid shape that we are trying to find the volume of, but it's not a solid cylinder, so it's a little bit harder to find the volume than normal. Okay, so yet again, okay, my radius is changing as I go from start to finish, and I'm adding up all of these circles. Like I have this circle, I have an infinite number of circles that I'm adding together to accumulate this area. So to show that, I wonder if this will do that for me. Let's say accumulate. Here we go. So here, what we're doing is we're adding up all of these circles together to create the volume of this entire cylinder, this entire vase, okay? So you start at 0, or A, and then you're essentially accumulating all of these circles over and over and over again, and then you get your overall volume. Okay, so let's look at some actual specific examples. I'm going to hit reset here and get that. Okay, there we go. So let's go back to our notes for a second. Okay, let's look at some examples. All right, so these are all called revolutions of solids, okay, or solids of revolution, volume by revolution, volume by rotation. There's a lot of different names, but basically you're taking a function and you're rotating it around an axis. And when you rotate it around an axis, it creates a solid shape that you can find the volume, okay? So let's talk about the region enclosed by y equals x squared, y equals 0, and x equals 2. Then sketch it rotated / revolved about the x-axis and find its volume. So y equals x squared is the quadratic equation. So let's change colors. Let's make it more interesting. Yeah, let's go with purple. So 0, 0, 1, 1, 2, 1, 2, 3, 4. So that is and up here. Okay. So oops. Got a little out of hand there. There we go. Ah, this is almost the same. Oh well. Okay. Enclosed by y equals 0. So that's the horizontal line or the x-axis. There we go. Y equals 0. And then x equals positive 2. So that's the vertical line here. So essentially we care about this piece, this area right here. Okay, that is the area enclosed by those three functions or those three equations. I want to sketch it rotated about the x-axis and find its volume. So let's think about this. If I were to take this particular shape here and I rotated it around the x-axis, okay, essentially if I were to look at this straight on, I would have the mirror image of it below. I would have right here, I would see the exact same image on the other side. Okay, let's look at this for a second. Does that look like anything familiar to you? It's a little bit skinny, but if you kind of like, if you were to look at this sideways for a second, that kind of sort of looks like, maybe like a Hershey's Kiss. It's flat on the bottom and then curved up on the sides. You guys see that? So this would be kind of a Hershey Kiss shape. Okay. So now I want to find the volume. How do I find the volume of a Hershey Kiss? Because that's not a normal cylinder. What the heck do we do with that? Okay, well, we're going to follow the same process that we set up a minute ago. Okay, so what we're going to do is we're going to go from beginning to end, so from A to B. In this case, A is 0, B is 2. Okay, now remember, we're adding up all of these circles. There's an infinite number of circles here, and the area of a circle is typically pi r squared, but in our case, it is now the function pi times the radius of x, a function of x squared. Okay, well, that radius in this case is the function x squared. So my volume is going to be pi times the integral from 0 to 2 of x squared with respect to x. Okay, this extra squared comes from this squared right here. This squared comes from the fact that my original function is x squared. That's why it's a double squared. Okay, so I've got the volume is equal to pi times the integral from 0 to 2 of x squared dx. And I can clean that up here. I'm going to just go ahead and make that x to the 4th. So I've got volume is equal to pi 0 to 2 of x to the 4th dx. This is super easy to integrate. I've got pi times x to the 5th over 5 from 0 to 2. Go ahead and use first fundamental theorem of calculus by plugging in the 2 and the 0. So pi times 2 to the 5th over 5. I know when I plug in a 0, I get 0, so I just write 0 here. So this is going to give me 32 over 5 pi. That is the volume of this shape that this solid figure that we created by taking y equals x squared and rotating it around the x-axis. Now the volume would have changed if we had changed the bounds over here, but this is what we would have gotten in this particular situation. Okay, let's try another example. Consider the region enclosed by y equals x over 2 minus 1, y equals 2, y equals 0, and x equals 0. Find the volume of the solid formed by revolving this region about the y-axis. Okay, earlier we were revolving around the x-axis. Now we are rotating it about the y-axis. So that's going to make things a little bit different, but the overall process is going to be very, very similar. So the first thing I want to do is go ahead and sketch all of these crazy lines here. So y equals x over 2, or 1/2 x minus 1, okay? That's essentially what this is. So 1/2 x minus 1, so slope-intercept is -1. Or, I'm sorry, my y-intercept is -1, my slope is 1/2. So I'm going to go up 1 over 2, up 1 over 2, and then down 1, like that. And then let's see if I can draw a nice straight line all the way through. Ah, beautiful. Look how perfectly straight that was. Okay, so that's that one. Y equals 2. So that's going to be this line here. Y equals 0. So that is going to be the x-axis here. And x equals 0, which is my y-axis. So, okay, the region that is enclosed by all 4 of those, 4 of those, is going to be this region right here. Okay, I'm not going to go below the x-axis because remember, it stops at y equals 0. So I'm taking this region right here and I'm rotating it about the y-axis. So when I rotate it, it's going to go this way. Okay, so then I would essentially have a mirror image of it going this way. Oh, that's not going to be quite. Make sure my slope is right. So over 2 up 1, over 2 up 1. Okay. There's a little bit better. So this is what the other part of it would look like. So imagine in your head that this was a solid shape. Okay, what kind of a solid shape would this look like to you? Or what kind of item would have this kind of shape? You could think of maybe a bowl would have this overall shape, or a pretty short plate. If you think food, maybe kind of sort of like a Reese's peanut butter cup. Oh, you guys see that? Because it's got the little edges right here. Reese's peanut butter cup. Yeah. Cue the Reese's peanut butter cups, by the way, if you haven't already got one. Okay. So now, because we are integrating this, we are revolving this around the y-axis, just like when we found area in terms of y, we had to find volume in terms of y as well, because we're rotating it about the y-axis, or just a vertical axis of rotation, okay? So since we are revolving around y-axis, we integrate, in terms of y. Okay, the last problem, we rotated about the x-axis, so we integrated in terms of x. Now we're going to do everything in terms of y. Okay, so now my radius, instead of being a vertical measurement, my radius is now this horizontal measurement, which changes as my y value changes. Okay, so I need to figure out, well, what is this function right here in terms of y? Or I guess I should say, what is my radius? My radius in terms of y. Well, I know what this curve is. I know what this curve is right here. This is a curve y equals 1/2 x minus 1. But that's in terms of x. I need it in terms of y. So y equals 1/2 x minus 1 becomes y plus 1 equals 1/2 x. So then multiply by 2. So 2y plus 2 is equal to x. Okay, so my radius itself is going to be, so my radius in terms of y, this is an r, is equal to 2y plus 2. So then my volume is going to be pi. Now, my a to b is going to be the bottommost point for my y value, which is 0, to the top, which is 2, so 0 to 2. And I'm going to integrate my radius squared, so 2y plus 2 squared dy. Again, pi radius squared. But remember, your radius changes. the entire time. So because the radius is changing the entire time, we're integrating it so that way it's accounting for all of the infinite little radii that occur from here to here. Okay. From here, it's just a pretty basic integral scenario here. I would go ahead and just multiply this one out. So volume is equal to pi 0 to 2. This is going to be 4y squared plus 2y times 2 is 4, but 2 of those, so 8y plus 4 dy. I'm pretty confident in our integration skills from this point forward, and I will tell you that the answer to this should work out to be 104 pi, or 104 over 3 pi. Okay, feel free to double check me on that, but I feel like that's pretty close. Okay, the main thing I want to focus on right now is just, can we set this up correctly? And then I know that you guys know how to integrate from here. Okay, let's try another one. I want you, like normal, pause the video, give this a try, see if you get the same thing we do. Okay, so if you've already done that, welcome back. Cool. Now let's work this problem. Okay, so we're considering the region in the first quadrant enclosed by y equals 4 minus x squared. So they only gave me one curve, but they're telling me that it's in the first quadrant. So essentially they're also telling me, hey, don't go outside the x and y axis. Okay, so 4 minus x squared, so 1, 2, 3, 4, over 1 down 1, over 2 down 4, 1, 2, 3, there we go. It's going to look like that. Okay, and I'm not going outside the x and y axis because I'm staying in the first quadrant. So I'm rotating this curve. Which direction did they tell me to rotate it? They're telling me to rotate it about the x-axis. So we're rotating it this way. So then the mirror image of that would be 1, 2, 3, 4 down here. And imagine a solid figure this way. Okay? What does that look like to you guys? Kind of, sort of. Looks like a mound. Okay, if you were to look at a mound from afar, like, you know, just like I don't know, a pretty smooth mountain-ish region, I guess. If you're thinking in terms of food, kind of, sort of looks like a Nilla wafer, if you think about it. Okay, you got this Nilla wafer right here, okay, because it's flat on one side and then kind of like a round. You see that? Okay, but let's find the volume of this, quote, Nilla wafer. Okay, so now I'm back to rotating it around the x-axis. So my radius is in terms of x. Okay, my radius is this curve right here. R of x is my radius. Okay, so in this case, R of x is going to be 4 minus x squared. So my volume is pi from 0 to 2. And I know that it's 2 just because I know that the curve 4 minus x squared crosses the x-axis at 2. If you didn't already know that, you would just find out where your x-intercepts are and then go from there. Okay. My radius is 4 minus x squared, but then I'm squaring that with respect to x. Okay, sorry about that. I'm coming back from a phone call. So let's see, double check here. So we've got the volume is equal to pi times the integral from 0 to 2 of 4 minus x squared. This is our radius. All of that squared dx. Again, to integrate this one, I would go ahead and just multiply this whole thing out, integrate from there, and then you should get 256 over 15 pi as your result. Okay, so that is how, and I'll have the filled in version on Canvas if you really need to figure out how to integrate that. But yes, that is how you would find the integral of that, or that's the answer to that integral. Okay, let's try one more. Okay, so let's say we took the exact same region that we just had enclosed by y equals 4 minus x squared. So let's go ahead and draw that again, 4 minus x squared. So boom, here we go. Same region that we had from before, but now instead of rotating it around the x-axis, we're going to rotate it instead about the y-axis. So it's going to go this way. So now it's going to create a completely different shape. It's going to go kind of like this. Boop, 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 boop. Okay, so now when I look at this, well, this no longer looks like a Nilla wafer. Looks like something a little bit taller, maybe. Kind of looks like a candy, like a dot, maybe. You know how those dots are kind of like flat on the bottom and kind of tall and stick up, kind of weird. Those little gummy things. Looks like a dot. Okay, so now let's go ahead and find the volume of this. But again, because we're rotating around the y-axis, our volume has to be in terms of y. So I need my radius, need my radius in terms of y. Well, right now I have y is equal to 4 minus x squared. I need this in terms of y, so I need to go ahead and solve for y here. So y minus 4 is equal to negative x squared. Divide by a negative. So then I have 4 minus y is equal to x squared. When I take the square root of both sides, this becomes x equals plus and minus the square root of 4 minus y. In the context of this problem, though, because I'm looking at just the first quadrant, in the first quadrant, my x values are positive, so I really only need to worry about the positive square root. Okay, so yes, I do have the plus and the minus, but I'm only going to use positive root 4 minus y for my axis. Okay, instead of calling that x, I could just call that radius in terms of y. Okay, so then I want to find the volume. So my volume, just like before, is from pi, or times pi, from my lowest y value is 0, my highest y value is 4, because remember, my bounds have to now be in terms of y instead of x. Everything is in terms of y. My radius is the square root of 4 minus y, all of that squared, dy. Now, luckily, the nice thing is for this one, whenever you square a radical, that goes away. So the integration for this one is probably the simplest one we've had in a while. And I'll tell you that this one should work out to be 8 pi. Okay, again, if you need to go back and rework it, check Canvas because I've got the filled-in version on there. Okay, I think I've got one more example. Let's see, consider the region enclosed by y equals x squared, y equals 0, and x equals 3. Find the volume of the solid form by revolving this around the line x equals 3. Oh, this time we are not rotating about the x-axis, or the y-axis. We are rotating it about the line x equals 3. So let's go ahead and sketch this out first. So y is equal to x squared, so 0, 0, 1, 1, 2, 1, 2, 3, 4. Let's go ahead and go over to 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's my curve. Y equals 0, so that is the x-axis. X equals 3, 1, 2, 3. Perfect, there we go. And so, okay, we are going to take this entire thing. Boop, boop, boop. Let's fill this in here. And I'm going to rotate this around the line x equals 3. So that's still going to be this way. Okay, x equals 3 is a vertical line. So now instead of mirroring it over the y-axis, I'm mirroring this region over this line right here. So I'm going to have, let's see, 1, 2, 3, 1, 1, 1, 2, 3, 4. So it's going to look like this. But we're rotating it this way. We're rotating it around the line x equals 3. Okay, so yet again, because I have a vertical axis of rotation, my radius must be in terms of y. All right, so my original curve was y equals x squared, but now I want that in terms of y. So I've got this plus and minus root y is equal to x. However, I'm only going to want the positive. So the catch, though, let's think about this. So I want so really I'm looking at this area right here. If I were to just look at this curve and I were to just do, if I were to say that my radius was simply root y, okay, that would be this curve right here, but that would give me this distance from the y-axis to here. That's not what I want, okay? I want the distance from this line back to this curve. That is the distance that I want. So remember, to find distance between two things, we just subtract them. So r of y is actually, in this case, going to be 3 minus the square root of y. Okay, that might have blown your mind for a second, so bear with me here. Okay, remember, this whole thing is the area that I am rotating. So these distances right here are all of the radii that I want. Well, the distance that I want is going to be this curve minus this curve. Well, this curve is 3 because x equals 3, and this curve is square root of y. So my radius is going to be 3 minus root y. Is everybody following me on that one? Okay, again, x equals 3 minus the square root of y will give me all of these distances here. If I were to just look at root y, that's all of this stuff. I don't want all of that stuff because I'm not rotating it around the y-axis. I'm rotating it around a different vertical line. So you can think of this guy right here is my axis, and this is my curve, okay? So a lot of times you can think of your radius as simply the axis minus the curve, okay? So the distance from the axis to the curve, that's going to be your radius. So now that I know that, I can plug that into volume. So pi, my lowest y value is 0, my highest y value is 9, my radius is 3 minus root y, and then that's going to be squared dy, okay? The integration for this one is a tiny bit messier, not so much. You're just going to go ahead and apply FOIL like you have been, and then I would make sure that I rewrite all of these in terms of like y to the 1/2, and then when you square it, y, you know, it all works out when you write it with exponents, okay? I will tell you that the answer to this one is 27 pi over 2. Again, I will have that one worked out on Canvas as well. The main goal here today is, can we set these up? Okay, so what I want us to think about now, we've done 5 different examples, okay? If I were to look at this shape right here, okay? Let's say I were to just like cut it in half right there. I cut it in half and I split the top with the bottom, okay? Well, the top and bottom pieces, if I were to just look at where I had the cut, I would have 2 solid circles, okay? We call those solid circles in the world of math, discs. Okay, so this whole thing, what we've done so far today, is what we call the disc method. This is the disc method for finding volume using, or for rotations of solids, volumes of revolution, things like that. Okay, when you have a horizontal axis of revolution, your volume is equal to pi times the integral from a to b of your radius. I use a capital R here. You could have also used a lowercase r. Either way is fine. Okay. And this is where your radius is in terms of x, but it's also that distance between the axis and the curve. Okay, notice I have this in absolute value bars. Depending on where your axis is, your curve could be to the left of your axis, so you might end up with a negative number. So we don't want that. We just want the distance between, and distance is always positive. Throw in an absolute value bar and you're good to go. Okay, basically you're going to square it anyway, so it doesn't matter, but for simplicity's sake, we throw in the absolute value bar. If you have a vertical axis of revolution, all of this looks exactly the same. It's just that everything is in terms of y instead of x. Okay, so you're going to have everything in terms of y instead of x. So this is called the disc method. And what's happening is when we take a shape and we rotate it about an axis, and if we were to do a cross section of it, it would be a solid circle. It would be a circle that has, like, it's just a solid disc essentially. Okay, so that is called the disc method. let's look at another example, but this one's not going to be the disk method. This is going to be an example setting us up for the other method that we have. Okay, so the other method we have, let's see, consider the region enclosed by y equals x squared. Okay, familiar function yet again. 1, 2, 3, 4. So here, and y equals x. So doot, and y equals x. Oh, this is going to be really hard to see. I'm actually going to like increase the scale here. Okay, so let's say that this 1, 2, 3, 4, this counts as 1 unit. 1, 2, 3, 4. This counts as 1 unit. So when I graph y equals x squared, I'm going to go all the way out to here. Okay, and then when I graph y equals x, now it's really obvious where these two regions come together. Okay, so technically these two lines do continue, or these two curves continue, but oh no. Whoa, if that's a 1, it's got to go over here. That's, whoa, not quite the same, but you know what, close enough. All right, so here's the region enclosed by both of those. Okay, I am rotating it about the x-axis. So I'm rotating it this way. So I would have a mirror image down here. Looks something like this. Okay, not gonna lie. Let's see. That could be a bowl type, a weirdly shaped bowl. What other kind of shape could that be? Oh, if you go to the mall, you know those things that you can like donate your coins and it spins around and around and around? Imagine like putting a coin here and it would just spin around and around and around until it gets to the bottom. Maybe one of those things, okay? Either way, regardless of the shape, now if I look at this, if I were to take, like, quite simply, if I were to just like cut it right here, cut this shape, would I still have the same solid circle that I had before? Well, the answer to that question is no, because I have this gap right here between these two curves. Okay, instead of having a solid circle, I would essentially have an outside circle and an inside circle, and then I would have this donut-y shape. Okay, that actually really does look like a donut. Okay, we actually don't call it a donut. We have a better name for it, but we'll get to that in a second. Okay, well, so now if I were to find the volume, I have to think about finding the volume. I have to find the volume of the outermost part, and then I subtract the volume of the inside part. Okay, so to do this, I'm going to say pi, let me label it here, volume is equal to pi times, so from A to B, so 0 to 1, 0 to 1, the outermost curve, in this case, so think of, like, when I say outside minus inside, let's think about this. Like if I were to actually, those vases we had earlier in class today that we talked about, okay? If I wanted to find it, look how beautiful that was. If I wanted to find the volume of like the water inside the vase, if I were to pour water inside the vase and I wanted to find the volume of all the liquid in there, then I would just do the disk method because I would have all of this filled in right here. I would have a solid shape. But let's say I wanted to find the volume of just the vase itself, like just this thin glass thing right here. I would have to find the volume from the outside and then take away the volume of the air in between, and that would give me the volume of just the vase itself. So essentially that's what we're doing. I'm finding the volume of the outside and I'm taking out the volume of all this inside stuff because I don't need the inside stuff. But if I were to find the volume of just this curve, I say curve, this line right here, that would find all of this stuff. Okay, I don't want that much stuff. I need to take the rest of it out so I just have the parts that I want. So basically I need to find my outside radius squared minus the inside radius squared dx. Okay, well in this case, so 0 to 1, my outermost radius is the curve y equals x, so that's going to be x squared. My inside curve was x squared dx. Okay, So then this just becomes the integral from 0 to 1 of x squared minus x to the fourth dx. And we know how to integrate that pretty basically. So this is 2 over 15 pi. Okay. Now I told you that this method would have a slightly different name than the last one, and it's because we had this hollow disk essentially. I don't want to say disk. Ooh, that's bad. Not disk. This hollow piece in the middle. It kind of looks like a washer. I guess we could have called it the donut method, but the donuts aren't really like flat like a washer is. And by washer, I don't mean like washer and dryer washer. I mean like nuts, bolts, and washers. Okay, for some of us who are like, what's a washer? Okay, if you still don't know, look up, Google like nuts, bolts, and washers. Okay, we're looking at the washer. When you have a horizontal axis of revolution, your volume is now pi times the integral from a to b. Now, notice I have r of x capitalized and then lowercase r of x. This is going to be the outermost radius minus the innermost radius. Okay, basically which radius is furthest away from my axis of revolution, and then which radius is closer to my axis of revolution. If you have a vertical axis of rotation, it's going to be very similar, only everything is in terms of y. Okay, so that was a lot for our notes today. Pretty lengthy set of notes. I understand you probably could still have some questions about this. That's totally fine. Go search out any other teacher that would have this knowledge. Also, you can check Prof. Rob Bob, Khan Academy, or even CalcView and CalcChat in your textbook. Both of those will help you out as well. So all those great resources, use those wisely.